Thanks, everybody. Thanks for having me. It's very exciting to be speaking here. Try and get my presentation on the road. So today I want to talk about some of the work that I do in the architecture industry. So my background is in mathematics, and I started working for structural engineers early in my second year of university through my math degree. And I was the first mathematician that they had sort of decided to hire as a joke, I would suspect, at the beginning. But I got quite infatuated with the geometry problems that came out of that work. And since then, I've been focusing almost exclusively on solving complex problems in architecture. So today I want to talk, at the risk of alienating myself from the crowd, I want to talk a little bit about the theory that underlies the work that I do, and then hopefully showcase some case studies. So I'm sure that a lot of these software platforms look quite familiar. These are I would say, and I don't think this list is comprehensive, but these are the software platforms that would constitute a professional office. These are the things that architecture gets delivered with today. The problem is, underneath all these software platforms are some very tricky bodies of knowledge in discrete differential geometry, topology, concepts like Gaussian curvature, mean curvature, stress tensor, for those of you who just come out of engineering school. These things underlie these software platforms. And it's my experience that an effective delivery of complex projects requires not just a mastery of the software platforms that you're using, but actually the knowledge that these software platforms are based on. So if you were to kind of distill those fields of research and kind of lump them together under some main headings, I think primarily mathematics would be a big one. You know, this idea of a model being composed out of discrete elements and manipulated in three-dimensional space, although virtual three-dimensional space, I mean, this is a large part of what mathematicians do and have been doing for the past, 200-300 years. The actual execution of these methods is quite tricky and requires a lot of knowledge of computer science, how software is actually written. Increasingly today, we have a lot of examples of live physics engines. These provide real-time collision detection, rigid body analysis. You can evolve complex structures, how they behave under gravity. A tricky thing to do as a basic structural analysis it's not that tricky, but it's a little trickier than you might think, is just to see if something's going to fall over. Right? And game engines and rigid body analysis provides that in a completely interactive and real-time way. So this provides a very kind of fundamental dilemma for the architecture, engineering, and construction industry. On the one hand, for the complex projects that you're faced with, you need this fundamental body of knowledge to execute and deliver the projects effectively. On the other hand, your office is composed primarily of, as you would assume, architects, engineers, and contractors. So how do you address this issue? A lot of offices have turned to hiring individuals with this skill set. You can get a mathematician in your office. That's what I was for 6 years, kind of the token mathematician. You can hire someone in computer science. The problem, though, is that these fields require connection to their larger bodies of research. These people need peers. They need situations similar to those found in universities, research groups, and a full-fledged kind of research program is unattainable for most competitive architecture and engineering offices simply because the overhead of hiring these people is too large. Imagine funding your own kind of like, NSERC grant. So with the problem also comes an opportunity, something that I've been quite interested in. And I believe there's a real niche for a new kind of service for the engineering industry, something that sits a little external to the standard consultants, is actually positioned between research and practice. This is something that could leverage a strong connection to academia while also maintaining one foot in the competitive industry. To kind of look at this in a colder light, I should say, anything you do with a 3D model, at the heart of it, we have some wonderful kind of booths out there that showcase innovative techniques and innovative software platforms for 3D models. But 3D models at their heart are not that complicated. You have a number of players, things like numbers, points, volumes, meshes, curves, surfaces, lines. At the heart of a purely geometric model, that's all you're ever dealing with. And if you were to kind of say, if you were to remove yourself from this kind of conference and this situation in general and just say, I need expertise with these things, chances are you would look to a research expertise such as mathematics or computer science. On the other hand, building information modeling had this wonderful idea, and you guys have all been through this BIM 101, so I'm not going to belabor this point, but it's worth putting up on the screen, that added addition to the classic players, the numbers, the points, the lines, you have all this metadata, things like the density of a material, quite concretely the Poisson ratio of materials, their cost, their location, suppliers. So added to these players, you add some new players. And the real ingenuity of BIM, I think, is the fact that you link these all together in a cohesive database. So I'm gonna get a little bit into the theory of why sort of geometry is so important to this process, and it comes out of this concept called discretization. And I'm not sure if some of you might have heard this term before, but so what happens is in architecture, in the digital model, it's quite easy to model sort of a really smooth and sexy surface for a roof. But at an architectural scale, it's very rare that anything actually curved gets built. And even if something curved does get built, the scale of their individual components is nowhere near the size of the overall construction. So a process called discretization has to take place, whereby you chop up the original surface or volume into its constituent parts. But this is quite tricky as it happens. You can think of the classic example of a sphere. You have a smooth sphere, and you want to map the chessboard pattern onto it. Well, you have a couple options. The bottom part of this picture shows some patterns that you can fold up and distort onto the sphere. And they all result in a discretization of the sphere. No longer is the sphere something totally smooth, but it consists of panels. Even if that discretization can be quite complex, you can try and apply it to increasingly complicated surfaces and try and factor in various manufacturing constraints, things like that. But there's a really deep connection with mathematics going on here. And that connection is, at the end of the day, regardless of what you use to discretize a smooth object, what you end up with is a set of panels. And more concretely, you end up with a bunch of vertices, a bunch of points, some edges, and some faces. So consider this little experiment. If you take a very coarse approximation of the sphere, so tetrahedron is very far from being a sphere, but it exhibits many of the same properties, and you gradually try and get something smoother and smoother. and you add up the vertices, you subtract the edges, and then you add the faces. You get the same number. This is something that Euler found out about 200 years ago. It's called the Euler Characteristic. And it has a fundamental connection between what it means to be curved and this very concrete notion of how many vertices, edges, and faces. These are how many panels, how many glass panels you have, how the support structure meets with those panels. So given a surface, if the Euler characteristic, this value has to be constant through whatever kind of discretization you care to approach, well, what does this mean for architecture? And so I love this slide. This is a Massimiliano Fuxas building. And this is a gorgeous panelization where they strove to create everything very, very regular. You have some very regular connections over here. As you merge into this concave shape, you have the regular connection of a triangular grid. You have one vertex and 6 connections. But remember, the Euler characteristic is fighting to be shown here. So what happens? Well, you have one giant connection here, where you have 1, 2, 3, 4, 5, 6, 7 connections. This, I think, shows this fundamental connection, because here you have a purely architectural consideration. I want mullions on a surface. But the inherent geometry of that surface forces you to have this connection detail. And that's a lot of the starting point for a lot of my work, is that how can you inform the underlying geometry to play well with manufacturing processes down the line. Okay, this is a project that I've been working on for the past couple months, and it's been publicly announced, and some of these renderings are like 2 days old, so I'm really excited to talk about it. The client is York University, and the lead architects are ZAS. The initial starting point was this pattern, originally introduced by Penrose, who's a famous mathematician. And they wanted this pattern to be applied to a doubly curved skin. There's some initial renderings where we tried to actually regularize the panelization as it gets mapped to this skin. But I'm sure many of you have tried to do this. There's a problem, and the problem is that it's impossible to exactly map a pattern that's been defined in the plane to a curved surface. And this has implications because patterns that are in the plane often exhibit really nice properties, like repetition of panels. You know, it's one thing to have 7,000 panels that are one of 3 types. And then when you map it to the surface that you're actually going to build, suddenly everything's unique. Everything has to be custom placed and custom manufactured. Let's get through that. But it turns out that you can leverage the small amount of play that's found in a lot of these facade units, the kind of 60 millimeters of construction tolerance. And you can leverage this tolerance to try and get back to something that's as repetitive as the planar pattern that this came from. And actually, I'll show a little app that we wrote to investigate this property. So the idea here, is that you have some planar arrangement of panels that work quite well. It's quite boring, but it works well. These are all repetitive equilateral triangles. And so this uses a rigid body physics engine underneath to keep these panels distinct and allow a little bit of play between them and to see what kind of shapes you can come up with. So if we adjust the braking force required to separate these panels, We can grab one, hopefully. Start to move it up. You can see as this guy moves up more and more, there's quite a bit of force imposed on that top panel, but we can get it back into the simulation, and you see that actually you get a quite interesting structure out of these very regular panels. And more than that, it's the physics engine underneath that's keeping these panels separate from each other. And so, of course, you need to have a bit of play between them. The idea is that maybe with a clever mullion detail or something like that, you can hide this play and achieve repetition in a very interesting way. As one more example, to get something a little bit smoother, you can keep the corners of this structure locked in position, but they're able to rotate. And then we can apply uniform upwards force on this and see how this evolves into a dome-like structure. Already the behavior of these panels is very unintuitive. I don't think anyone could have sit down and draw this structure. So right there, you have something that's significantly curved, leveraging the play between these panels. You can also, if the various amount of tolerance between the panels is too large, you can adjust it and go from there. So we applied a kind of grown-up version of that simulation to this project. The starting point for us is typically the smooth underlying surface, where our task was to initially to map this pattern that they had defined in the plane onto the surface with all its imperfections and distortions. And it's a bit difficult to see here, which is maybe a good thing. But between this slide, where every panel is actually unique because of this distortion, in this slide, although there's some folding similar to what you just saw, but to a much lesser extent, you can maybe see it over here, each panel is one of 3 types. So there's 7,000 panels here, and you can mass produce 3 types, and everyone will fall into one of these 3 types. Of course, this doesn't adhere to the boundary condition, which is always an issue. So we use 10% of those panels to accommodate the boundary condition and achieve repetition of 90% throughout the other panels. Again, repetition meaning that each panel is one of 3 types. And in the end, these are some work in progress renders. More than that, because we now know exactly where all the panels are in space, although we've used the play between the panels to position them there, we know exactly where they are. And to assemble this system, you can grab one line that corresponds to a floor plate and precisely position one band of these panels. So maybe that might be 10% of the final thing. But the point is, because of their slight offset position, the rest of the structure is self-jigging. Every panel has to be one of these 3 types, so there's one position that the panel can fit given its predecessor. So this means that you can fairly efficiently construct these types of facade assemblies without having to laser scan every single panel. So the second competition we actually did, we wrote 2 different apps to help the design process. So the first one wasn't a competition. That was a real project. This one is a much more speculative competition. From the architect, we had these really interesting concept diagrams where they wanted regular structures that evolve in surprising ways. Things like this, where Michael Meredith's projects with just sort of throwing lots of cubes into space and seeing what happens. Again, these things look very natural in the sense that we've seen these structures when, kids' toys and things get knocked over. But it's worth mentioning that to explicitly model these is very, very difficult. You have to evolve them out of physical processes. So we had some initial efforts where we tried to take individual residential units and position them in interesting ways and rotate them around and try and find a kind of interesting envelope. We quickly decided that what was needed is a little bit more of an interactive approach. It was quite time-consuming to individually place these units exactly where we wanted them to, with the additional constraint that these blocks had to be interwoven. So for this, we created another little app that starts off with the basic arrangement of this thing, with the ability to grab a hold of it, any one of these blocks, and you can just start sort of pushing and pulling them around. More than that, you can provide, global explosive forces to them. These are all just conceptual forces, just forces that aid you in the modeling and the form finding of these arrangements. Again, the point is that with these custom-built apps, with this access to the underlying workings of these programs, you can create tools that will allow you to design things that are very unintuitive, things that you would not have come at from a different angle. And this one actually has an interesting connection. It allows you to export an OBJ file, and that'll get you back into your regular modeling production pipeline. As another study, separate to the geometry, we wanted to figure out how people would actually interact with this study. And for that, we wrote a little crowdsourcing, or a crowd flow engine, which we've actually brought to a more production-ready level, but this is the demo program that allows you to build up entrances, ingress points, allows you to give an exit, and most interestingly, it allows you to give the structure and the agents that will navigate it, allows it to give points, or goals. So these yellow disks represent regions that agents want to navigate. These might be programmatic regions that you say you want to go to the gift shop. People coming into an art store or an art gallery eventually want to go to the gift shop. I do. But you can start to codify that relationship. You can create obstacles. Every floor plan really has some walls. Create a few more. And then, in terms of the interactivity, you can start spawning these agents. And you get a whole bunch of them going. So they're quite determined. They will find these goals. They will get to that gift store. The point here is that this kind of approach allows you to see things, patterns in your floor plan that you might not otherwise have access to. It looks like they're running. So that's beta software. We'll get there. So with all that kind of information that we whipped up quickly, we evolved this design towards something, that doesn't look all that surprising from the starting point, but it's the knowledge that was involved in the process from going from A to B that's quite exciting. So you can easily think that this specific arrangement is something you could have found by hand, but the designer we were working with was exposed to a huge array of these things that you could just sort of pick and choose from and start preferencing certain parameters over others. And it's this access to knowledge that I think is most valuable about this approach. Some final renders. So to kind of bring it back to where we are now, I think, from walking around in the other room and seeing, the offerings of software companies, I strongly believe that the future of this building information modeling movement is a very modular approach. It's kind of small prototypical bits of code that are specifically written for your project and for your needs, rather than large overarching software platforms. And so I've been very excited about that prospect, and I hope to continue work on that as time goes on. So thanks very much.
You mentioned that you're trying to bridge between, sort of bring it down to the practice level. So many of us here are practitioners. What do you typically see as a sort of timeline? How would you see interfacing with architects around these issues? What are the challenges that you faced in bringing this kind of thinking? Because I think it's got great validity.
I mean, in general, earlier is better. I find that when a project is open in concept and in time, it's a much more fertile ground for the development of these tools. Again, the whole point is to provide access to knowledge and access to a larger design space. And if you can have that up front, then decisions down the road will be much easier to make, equipped with that knowledge.
Jay Poling, Solicat. So, Daniel, are you working with any curtain wall manufacturers or any sort of fabricator level people on using this concept?
Yeah. So on the York University project, I work quite closely with the glazing manufacturer to continually vet these designs, and that's a big part of it. None of this can exist in isolation. I think often these panelization studies are brought only to the geometry level, and they're never really vetted with manufacturers. So we try very hard to work closely with manufacturers on all this stuff. Yeah.
Tom Strong with Illuston. So with the apps that you're developing, it's Mac based. Like, can you describe a little bit of the process you go through with coding, the type of code you use, the kind of hardware, software, who's involved, that sort of thing?
Yeah, great. So, I mean, in terms of the production process, we write it all in-house. Really, the goal for us is to provide this knowledge in the same way that software as a service is being provided. So. This doesn't mean a fully polished app that you can go on to resell, but rather something that just gives you the ability that you need right then and there. So we focus on quick turnover, quick prototyping, rather than extended testing and things like that. We're totally platform agnostic, so it's Mac, PC, Linux, if that's what you want to do. And we also write iOS, Android, web apps, anything like that. It's largely .NET based, largely C#, but within that we have a lot of C++ native code, native plugin access, so we can generally use any SDK that's out there.
Hi, Mike Laurie with Planet Measuring. One of our biggest struggles is once we create a building information model, whether it be in Revit or whatever, is allowing access for non-Revit users to get information out of that model. And we've been looking at this, you've verbalized what we're kind of doing is segmentizing, pulling out little bits of information with little scripts we're writing, but nothing as extensive as this. But is that something you can work on as well, as being able to pull or create little applications to pull data out of
Yeah, absolutely. I mean, I think, again, the huge power of BIM is the database structure. This is something that is maybe not put in the spotlight quite enough, but another area where databases have taken off in a big way are server-side web applications. And given a clever database construction, you can easily give user access, you can define queries that return only the public information. And more than that, the apps that we design can sit nicely on the web, so you could get a full kind of 3D interactive environment that queries your database for only the information that you want to expose. So yeah, it's definitely a possibility, yeah.
Jackson Fung from Contract Architect. Can you talk about the process and the collaboration between your study with the actual architectural documents? Like, how does that work, and how do you transfer those data into the
Yeah, so, I mean, the general answer to that is we try and fit right into existing production pipelines. You know, I have maybe my own ideas about project delivery, but ultimately our clients have something set up. And it would be very detrimental if we were to upset that process. So we, at the outset of all our projects, we try very hard to get a sense of where we can fit in, what exactly the product is that they want, and deliver that in a consistent way. So, I mean, a lot of my clients, it's just a 3D model. It's like, maybe it's just a Rhino file. But behind that Rhino file is this whole kind of armada of plugins and apps that we track and use to create that file. So on the FTPs, there's a single updated file that consistently evolves over the course of the project. Yeah.
Daniel, thank you very much. It's very informative and exciting stuff, and we look forward to seeing you as part of our industry even more.
Great. Thanks very much.